How could Newton decipher gravity? It was adequate to allow us to fly from the Earth to the Moon anytime. Get yourself lost in the ticking hands of time. Considering whether how we may decipher, it is basically the tip of the transient chunk of ice on its head. His disclosure isn't just a speculation. A key could open the approaches to the insider secrets of the universe, uncovering a universe more flighty and moving than we at any point contemplated. Imagining how does Brian Cox's new theory challenge our regular comprehension of time, and what are the possible ideas for our view of reality? Join us on an interesting examination through the documents of time itself, as we dig into Brian Cox's recently uncovered exceptional speculation on the idea of time in the immense universe around us. Secrets are ready to be uncovered, and a portion of these insider secrets include confounding things. Finally, gravity, which are essential pieces of our world. Envision an existence where time acts strangely. Can, all things considered, be delayed down or speed up? Furthermore, the power that keeps us on the ground may not be what it seems to be. This is the domain of Albert Einstein's hypotheses of relativity, where how we decipher time and gravity drifts off in surprising directions. Albert Einstein, an outstanding name, provided us with a superior perspective on the universe through his hypotheses of relativity. His work laid the foundation for understanding how time acts under different conditions, especially when going at mind-blowing high rates. It all began in the mid-20th century, at the point when Einstein proposed two weighty hypotheses: the special theory of relativity and the general theory of relativity. The special theory of relativity, published in 1905, changed how we decipher presence. In simple terms, it lets us know that the laws of physics continue as the same for all observers who aren't accelerating, no matter their movement. This theory presents the chance of relativistic effects, including the notable thought that time can grow or dial back under particular conditions. One captivating psychological study used to explain time dilation is the light clock. Imagine being inside a spaceship moving unimaginably fast, almost at the speed of light. Inside the spaceship, there's a light beam bouncing between two mirrors, opposite to the course of movement. As indicated by the laws of physics, the speed of light is constant for all observers, so the light bar should seem to travel an inclining way. Now, here's the intriguing part. The time it takes for the light beam to travel its way should be the same for both the observer inside the spaceship and the one outside. However, since the path is longer for the external observer, maybe it would take greater time for the light to finish its journey. This apparent time difference between the two observers is what Einstein called time dilation. Time dials back for the observer moving relative to the fixed observer. So, in this present situation, time acts differently depending on your movement. Grasping how things change when they move fast, known as relativistic effects, isn't simply a theoretical thought. Researchers use huge machines called particle accelerators like the Large Hadron Collider to make particles travel really fast, almost as quick as light. When things move this quickly, we need to think about time in a different way to make precise forecasts and estimations. Albert Einstein developed the special theory of relativity in 1905, and it changed how we see the universe, especially when it comes to time and movement. This theory challenges what we could normally think. It says that the laws of physics are the same for everybody, whether they're moving or not. This is different from our regular experience, where we could think that if something is already moving and we add more speed, it just gets quicker. However, Einstein's theory says there's a maximum speed that nothing can surpass. This is the speed of light. From this point of view, events that appear to occur simultaneously for us may not appear that way for people moving near the speed of light. Another outcome of this new way of seeing things is length contraction. This means that if something is moving, it looks shorter in the direction it's moving when you observe it from a spot that isn't moving. Then there's the famous equation, which comes right out of the special theory. It demonstrates that energy and mass can be converted into each other, which is crucial for understanding how small particles act while they're zooming around at very fast speeds, and also for things like what happens when particles split in atomic reactions. Special relativity isn't just a theory. It's something we use in ordinary technology, like GPS. When GPS satellites send messages to your device, They're moving, so time acts a bit differently for them. If we didn't account for this time dilation effect in our GPS calculations, your navigation would be wrong. So, special relativity tells us that time isn't the same for everything and everywhere. It really depends on how things are moving. This idea challenges what we think we know about reality. It's like saying our ordinary understanding of the universe is a bit off. According to the special theory of relativity, time isn't fixed, it's affected by movement. Some key ideas, like the speed of light always staying the same and how energy and mass are related, have been proven by countless experiments. But there's more. Enter Albert Einstein's general theory of relativity from 1915. This theory dives deeper into the connection between gravity and the structure of the universe. It overturns the old idea that gravity is only a force that pulls things from a distance. Instead, it tells us that gravity occurs because space-time itself is bent or warped. It's like saying, hey, gravity isn't some strange force. It's just how things naturally move in the universe. According to Brian Cox, understanding general relativity means thinking of the universe as a four-dimensional thing, combining three aspects of space with one of time. In this framework, huge things like stars, planets, and even us impact how space-time is shaped around us. Imagine space-time like a big, stretchy blanket. When something heavy like Earth is placed on it, it creates a dent. If you place something smaller like a ball near Earth, it will move toward the dent. This is how objects act due to gravity, not a baffling force, but a response to the bending of space-time. It's like Earth makes a little divot in the space-time blanket, and things move according to that dip. General relativity gives a strong explanation for how things move in our solar system, like how the planets orbit the sun. It can precisely tell us the paths these planets take, including how Earth follows an oval-shaped orbit around the sun. According to Brian, this is different from the old idea of gravity just pulling things, which struggles to explain how planets move the way they do. The new idea is that realities are bent like a flexible fabric, and that fits better with what we observe. A pivotal moment that confirmed general relativity was correct happened during a solar eclipse in 1919. Sir Arthur Eddington led a team to see how light from distant stars bent as it passed near the sun. According to the theory, the sun's massive mass would make the starlight bend a bit. During the eclipse, the observations precisely matched Einstein's predictions, establishing the validity of the theory. Continued to make groundbreaking discoveries based on Einstein's theories. The detection of gravitational waves was a monumental achievement, confirming that space-time itself can stretch and ripple, just as general relativity predicted. This discovery not only validated Einstein's work, but also opened up new ways of observing the universe. For instance, the ability to detect gravitational waves allows scientists to study cosmic events that are invisible to traditional telescopes, such as black hole mergers and the collision of neutron stars. As research progresses, physicists continue to explore the farthest reaches of our understanding of time, space, and gravity. Brian Cox's theories, like Einstein's, challenge us to reconsider the very fabric of reality. They push the boundaries of our knowledge, inviting us to think in new ways about the universe's origins, its structure, and the forces that govern it. The exploration of time and gravity, whether through the lens of special relativity, general relativity, or newer theories, opens up endless possibilities. Each discovery brings us closer to understanding the true nature of the cosmos. In conclusion, the journey through time and gravity is an ongoing quest, one that connects the work of great minds like Newton, Einstein, and Cox. Their theories reshape how we perceive the universe and our place within it. By continuing to unravel the mysteries of time, space, and gravity, we pave the way for future generations to unlock even deeper secrets of the universe, one discovery at a time. The key to understanding the cosmos may lie in the very fabric of space-time, waiting to be uncovered by the next generation of physicists and explorers. Led various tests to check if general relativity is right, and each time it has demonstrated to be exact. Whether it's perceiving the way that planets move, the twisting of starlight, or recognizing gravitational waves, the hypothesis has reliably been upheld by proof. while saying gravity is completely wrong might astonish, particularly since we all encounter gravity consistently in the universe of physics. It's not unexpected to examine and research various ideas. Researchers like Brian often challenge established speculations, and with gravity, certain individuals question the ordinary way we ponder this fundamental force. One hypothesis testing traditional gravity is called adjusted Newtonian dynamics, (MOND), which proposes that gravity acts differently at low speeds, particularly in universes without requiring dark matter. Rather than adding undetectable matter, MOND proposes that gravity becomes stronger at low speeds. The gravity debate also includes puzzling dark matter and dark energy, introduced to make sense of certain peculiarities in space. Critics contend that these may not be essential, and alternative ideas can explain what we observe. Some scientists who disagree with Einstein's gravity hypothesis explore other possibilities, such as theories involving unknown particles or forces that could adjust or add to our understanding. It's important to understand that in science, groundbreaking ideas aren't ignored. They are painstakingly tested to see if they make sense. For instance, Einstein's concept of time in four-dimensional space, where time travel into the past might be limited by the speed of light, has been technologically explored, alongside ideas like wormholes and shortcuts. Stephen Hawking's order of security conjecture suggests that time travel into the past seems impossible from a physics perspective. Continuous tests and observations check if these new theories can explain things like the strength of gravity, in addition to what we already know. While alternative theories have been discussed, none have convincingly replaced the deeply grounded principles of gravity. Addressing and testing ideas are integral parts of how science learns new things, leading to further investigation and a better understanding of the universe. In the realm of gravity, Einstein's general relativity remains the most significant and effective one. Despite challenges and alternative ideas, it consistently performs well in tests and explains various phenomena, like how planets move and how light curves around large objects. General relativity remains steadfast because it's simple and covers a wide range of phenomena. As we discussed earlier, Einstein's general theory of relativity suggests that time can behave differently depending on how you're moving. Now, let's explore how this idea affects real-world scenarios, particularly in space travel. Space travel is exciting, but challenging because space is vast, and according to Einstein's theory, the speed of light is the fastest anything can go. This makes traveling between stars a gigantic challenge. Indeed, even with cutting-edge technology, the significant time frames involved in reaching the closest stars make space travel difficult. Consider the famous twin paradox to understand what happens with time when you travel in space. Imagine this. One twin stays on Earth, and the other twin goes to a distant star. When the space-traveling twin returns, they find that less time has passed for them than for their twin on Earth. This means they sort of traveled into the future. Time is essential for space explorers, because the longer the journey, the more time slows down. If astronauts travel to nearby stars where time slows significantly, they may age more slowly than people on Earth. While it may seem like science fiction, it's a real effect from the theory of relativity. Imagine if humans sent a crew to a star system not too far away. Since it's such an immense distance, the journey could take many years, even if they travel fast. For the astronauts on the spacecraft, time would feel slower due to time dilation. Meanwhile, on Earth, much more time would have passed. Time dilation not only affects living things, but also impacts technology. Computers and communication systems on spacecraft need to account for time dilation to ensure accuracy and proper functioning. Space travel challenges at high speeds include physical aspects, such as prolonged isolation and exposure to infinite radiation, as well as the mental effects of being away from Earth for an extended period. In our daily lives, we can see the effects of time dilation in the Global Positioning System, GPS. GPS relies on the precise timing of signals from moving satellites. Since these satellites experience time dilation, it's important to account for these effects in GPS calculations. Failing to do so would significantly impact the accuracy of navigation systems. Now, let's investigate why time moves in a single direction. Time governs our lives, moving from the past to the present and into the future. This one-way progression of time is fundamental to our reality. But why does time have this one-way nature? To understand, we look at entropy, a concept that measures disorder or randomness in a system. Entropy is tied to the arrow of time, and it tends to increase over time, causing time to flow in one direction. The second law of thermodynamics expresses this relationship, stating that in any closed system, total entropy will either increase or, at best, stay constant. In simple terms, entropy naturally tends to increase and doesn't decrease on its own. Understanding how things get more disordered around us helps us grasp the one-way movement of time. Imagine a deck of cards perfectly ordered. If we shuffle them, they become messy and random. This shift from order to disorder illustrates how time moves in one direction, as seen in everyday phenomena like ice melting or a stirred cup of coffee becoming chaotic. This flow of time works differently at different levels. If we look at small particles, the laws of physics allow things to move forward and backward in time, a concept known as time reversal symmetry. The disparity between this and the irreversible changes we observe in the world comes from something called initial conditions. The vast, complex world we live in is the result of many particles and how they interact, creating a one-way arrow of time. This idea of time moving in one direction is not just about ordinary things. It's also evident on a cosmic scale. The entire universe has been evolving in one direction since the Big Bang. The universe started in a low-entropy state, and over billions of years, it has become more chaotic, forming galaxies and stars. Scientists are still trying to understand why the universe began in such an ordered state. Even in the tiny universe of quantum mechanics, which deals with subatomic particles, there's an arrow of time. The way particles change over time appears to be even, but when we observe them, things become irreversible. Brian believes that it's not just a physics thing. Our minds also experience time in one direction. We remember the past, embrace the present, and contemplate the future in a sequence. This mental arrow of time is connected to how we perceive the external world's arrow of time. This concept of time has significant philosophical implications, testing how we understand reality. Time is an essential part of how we experience life and make sense of our world. Time dilation, as explained by Einstein's theory of relativity, has already been experimentally confirmed in various situations, such as in the behavior of particles traveling at high speeds or through precise GPS measurements. The principle is well understood, and its effects are observable even with current technology. However, translating this principle into practical time travel for astronauts is still an enormous challenge. While astronauts may experience time at a slower rate when traveling at relativistic speeds, near the speed of light, the technological limitations of achieving such speeds are immense. The energy required to reach such velocities is far beyond our current capabilities. Additionally, the immense radiation risks, exposure to cosmic rays, and the physical strain of long-term space travel would need to be addressed. In theory, if we could build spacecraft that could approach the speed of light, astronauts on board would experience time passing much more slowly compared to those on Earth. After a long journey, when they returned, they could find that centuries had passed on Earth while only a few years had passed for them. This phenomenon is often referred to as time travel into the future. However, time travel into the past, as proposed in some theoretical models, remains a subject of debate. General relativity allows for some solutions, like wormholes or closed time-like curves, that might permit backward time travel. But these ideas raise paradoxes, such as the famous grandfather paradox, and require conditions or materials that we currently cannot even detect, like negative energy. In conclusion, while time dilation provides a fascinating glimpse into the potential for time travel into the future, significant advancements in technology, energy generation, and our understanding of space-time would be required to make such a journey feasible. The idea of time travel, while theoretically possible, remains a distant prospect for humanity. The exploration of relativity, the nature of time, and the future of space travel will continue to inspire scientific and philosophical inquiries for generations to come.